So in the last class, we looked at this problem of power allocation across Gaussian channels, wherein we have a total power budget, and the goal is to allocate parts, this power across, say, M sub-channels or M channels, each with a different level of noise, so that the overall transmit rate is as large as possible. So we have a basic result from information theory, which says that if I allocate pi amount of power to a channel with noise variance sigma I square, then the maximum rate at which I can transmit, the throughput that I can achieve across in that particular channel, is half log 1 plus pi by sigma square, right? So our goal is to ultimately maximize the total throughput, which is the sum of the rates or the sum of the throughputs across different channels, right? And we have to do all of this while satisfying the total power constraint, that summation I equal to 1 to m pi is less than or equal to p, correct? So we were trying to analyze this particular problem. So what is the objective function? The goal is to maximize the total rate, which is the same as maximizing this particular quantity, summation I equal to 1 to m log sigma I square plus pi, right? Because the rest of it is just a constant which does not really depend on the pi's. And we basically have two types of constraints. One is that the power allocated to each channel should be non-negative. And the second constraint is, of course, the total power budget. The total amount of power that I can use is at most P. Right? Now, here, well, this is a maximization problem, but this is also equivalent to minimizing the negative of summation I equal to 1 to m log of sigma I square plus pi. Right, so minimizing this is our objective. So we can write the Lagrangian, which is actually the negative of summation I equal to 1 to m log sigma I square plus pi. So this is the negative of the total rate plus, well, I have two constraints. One is that summation I equal to 1 to m pi should be less than or equal to p, or summation over I pi minus p is less than or equal to 0. So I'll have a Lagrange multiplier for this particular constraint, the total power budget. And I have another set of Lagrange multipliers to satisfy the constraint that the power allocated to each channel should be non-negative. So that's the negative of lambda 2 transpose P. Okay, so now let's compute the KKT conditions. What does the first condition say? The first condition says that the gradient of the Lagrangian should be equal to 0. With respect to all the primal variables, they should be equal to 0. Right, so the first condition we have is that minus 1 over sigma I square plus pi plus lambda 1 minus lambda 2i should be equal to 0. And this is the same as saying that lambda 2i is equal to lambda 1 minus 1 over sigma I square plus pi. Right? And this is true for all I. Now we have some more conditions. So for example, we know that lambda 2 should be component wise greater than or equal to 0, right? Which implies that lambda 2i should be greater than or equal to 0 for all I. Or in other words, lambda 1 minus 1 over sigma I square plus pi should be greater than or equal to 0 for all I. Yeah. One upon the first one. So it's 1 over sigma I square plus pi, right? Yeah, so it's the negative log of this, right? So we're trying to minimize the negative of summation log sigma I square plus pi, because this function is convex, right? So ultimately, we want to first convert a problem to a minimization problem, and then compute the Lagrangian and the Lagrange dual function, and then evaluated the KKT conditions. So corresponding to this, we have minus 1 by sigma I square plus pi plus lambda 1 minus lambda 2i equal to 0. And that effectively gives us that lambda 1 minus 1 over sigma I square plus pi is greater than or equal to 0. Okay, what are the other conditions? We have that lambda 1 is always greater than or equal to 0. And we also have the complementary slackness conditions, which says that lambda 1 times summation I equal to 1 to n pi minus p, this should be equal to 0, which implies that either lambda 1 should be 0 or this quantity inside should be equal to 0. And lambda 2 transpose p, right? So the other constraint is this quantity should be equal to 0. Right? Or this is the same, but we know we also have an expression for lambda 2, right? So this implies that lambda 2i pi like there's something more that I can say. So this should be equal to 0 for all, because each pi should be equal to 0, because each pi should be greater than or equal to 0. Okay, but I already have an expression for lambda 2i, right, which is what I had over here. So lambda 2i is lambda 1 minus sigma I square 1 by sigma I square plus pi. So pi times 1 by so that's lambda 1 minus 1 by sigma I square plus pi. This should be equal to 0. Right? So this means that only one of these can be non-zero. Either pi should be equal to 0 or lambda 1 minus sigma I square plus pi should be equal to 0.
Was it not lambda 1 plus 1 by sigma square plus?
Sorry?
So lambda 2,
So
lambda 2i is equal to.
right, so we want to first convert this to a minimization problem, which would be minimizing the negative of summation I equal to 1 to n. So that's why you have the negative 1 by sigma. Right, so that was an error that I made in the previous class, because I started with a maximization problem and then tried to construct the Lagrangian from that. But what I should have instead done is taken the negative of that particular function so that it becomes a minimization problem, and then look at the Lagrangian of that particular problem. So it's lambda 1 equal to sigma I square plus pi, or what is pi equal to? Yeah, 1 by lambda 1 minus sigma I square. Okay, are there any other KKT conditions that I missed out? Well, the gradient is something that we looked at in the first point. The lambda should be greater than or equal to 0. We have the two complementary slackness conditions. And then anything else? Anything else? Not sure if this is visible. Oh, you want the object. Okay. Right. So the other condition is that the constraint should be satisfied. Right. So each pi should be greater than or equal to 0. Lambda 1 is a scalar. Lambda 2 is a vector. So that is why I've been using the underline for lambda 2 and just lambda 1 for a scalar. Right. So basically this is a combination of n different constraints, right? So p1 greater than or equal to 0, p2 greater than or equal to 0, up to pn greater than or equal to 0. For each of those I have a Lagrange multiplier, and I also have a Lagrange multiplier for the total power constraint. So I have n plus 1 Lagrange multipliers, and I've used this notation that the first Lagrange multiplier corresponds to the power constraint, and the remaining n Lagrange multipliers impose the non-negativity constraint. Right, so I also want pi greater than or equal to 0. So if I combine this condition with these two conditions, effectively what I get is that pi equal to 0 if 1 by lambda 1 minus sigma I square is less than 0, and it's equal to 1 by lambda 1 minus sigma I square if 1 by lambda 1 minus sigma I square is greater than or equal to 0. Which is the same as saying that pi is equal to the maximum of 0 and 1 by lambda 1 minus sigma I square. Okay, now we have one more constraint, and that is the total power constraint should be set. So effectively, well, so right now we have each of the PIs, but there's still one more variable left out, right? Lambda 1. And we somehow want to get rid of this lambda 1. And to get rid of this, you look at the other constraint that we have. We want summation I equal to 1 to n. Pi should be less than or equal to p, but if you look at this, effectively what we get is that summation pi is equal to p, because that's kind of natural. if you want to maximize the rate, then effectively you have to also use up all the power that you have. Because if you left a little bit of it if you have left some of it unused, then you could use that to increase the rate even further. So this is summation pi equal to p, or effectively summation I equal to 1 to n, the maximum of 0 and 1 by lambda 1 minus sigma I square should be equal to p. Now this looks like a sort of a funny looking expression. So effectively we have solved the problem, right? You just find that lambda 1 for which this particular quantity is equal to p, right? And this has a nice interpretation. So suppose I kind of draw a bin for each channel, right? There's one slot, this is channel 1, this is channel 2, this is channel 3, and this is channel 4. And I draw a bar for each of these channels. The height of the bar is basically equal to sigma I square. The height of bar I is sigma I square. Okay, so this is sigma 2 square, so sigma 1 square, sigma 3 square, and sigma 4 square. Right. I'll mark a point on the y-axis, and that is 1 over lambda 1. Right. Some quantity, lambda 1. This is 1 over lambda 1. Then what is the power allocated to the ith subchannel equal to? It's basically the difference between these two, right? 1 minus lambda 1 minus sigma 1 square, which is basically this particular height. This is P1, this is P2, this is P3, and sigma 4 square is too much. So P4 is basically equal to 0, right? Now, this has this interpretation of filling water in these slots, right? So the total amount of water you have is basically P. You can think of this as P. And 1 over lambda 1 is basically the height of the water once you poured all the water into these slots, right? So if you start pouring water in, what will happen? First, the slots at the very bottom will get filled. Right? So if my 1 over lambda 1 were equal to this, then only the first slot would get filled and nothing. If I increase the amount of water I have, that is the total power that I have, then it's not optimal to only use the best channel. You also have to use the second best channel. Right? So it's filling water up to this particular level across all channels that are available. And you keep increasing. So this kind of tells you that that it's not always optimal to only use the best channel when you have sufficient power. So using the best channel makes sense only if the total power that you have is so small that you cannot basically utilize the other channels effectively. So this is what is called the water filling solution. So the total volume, the sum of these powers, that is equal to P, the total volume of water that you have. Any questions? Yes.
We consider that strong duality
Correct.
is strong.
Correct. Yes.
Assuming
We're assuming that strong duality holds. In this case, it does. So this is, in fact, it's a convex optimization problem, and it also satisfies the constraints that we require for strong duality to. That's of course something that we've not explicitly checked, but in fact that holds.
So when we define pi is equal to 0 or 1 by lambda 1,
Yes.
how do we get those conditions?
So I've basically combined these three conditions, either pi equal to 0. So pi can either be equal to 0 or equal to this. And pi must be greater than or equal to 0. If 1 by lambda 1 minus sigma I square is less than 0, then obviously this cannot be satisfied. And obviously I can't choose a pi greater than 1 over lambda 1.
Not valid for those problems.
So, well, you can ask, okay, what do you mean by KKT conditions not holding?
Suppose the optimization problem.
Yes,
doesn't have this
correct. It's not strongly dual. Yes.
So this KKT condition.
So of course you're solving the dual problem, and whatever you get will ultimately be a lower bound on the optimum value. That's the only thing you can say.
So even if 1 by lambda by sigma square is greater than 0,
Okay.
why does pi have to be that? It could be 0 also.
Why does it? Okay. So either that has to hold, or so you're saying 1 over lambda 1
Even
over
if this
lambda
is
1.
positive, why does pi could be something doesn't have pi could be 0.
Pi could be 0. So suppose okay, so if pi equals 0, going to violate one of these conditions. Where use pi. So in this case,
1 over
lambda 2i can be, there's one more condition I believe that we have to use, and that is lambda 2i should be greater than or equal to 0. Case is greater than or equal to 0. Let me see if the second condition is valid. Is non-negative. Then you have lambda 1 minus 1 over sigma I square. That's okay. That's always greater than or equal to 0. Yes.
We know that 1 over lambda 1 minus sigma square is greater than or equal.
Yes.
So that lambda 2a will be something.
But yeah. So if I choose pi is correct. That's what I was looking for. If I know that if the following condition holds, that 1 over lambda 1 minus sigma I square is greater than 0, right? So suppose 1 over lambda 1 minus sigma I square is greater than or equal to 0, then what does this say about, so this, in addition, I also want lambda 2I, which is lambda 1 minus 1 over pi plus sigma I square to be greater than or equal to 0, right? But what does this tell me about lambda 1 minus 1 over sigma I square? Lambda 1 minus sigma I square is, sorry, lambda 1 is greater than or equal to sigma I square, right? Or 1 over sigma I square is greater than or equal to 1 over sigma I square is greater than or equal to lambda 1, right? Or lambda 1 minus 1 over sigma I square is less than or equal to 0. So if I choose pi equal to 0, then this constraint will not be satisfied, lambda 2I being greater than or equal to 0. So I have to choose, so I cannot choose pi equal to 0 if this condition is satisfied. It has to be strictly greater than 0.
K is equal to 0 would mean that both the terms.
Which one?
If you take K is equal to 0, both the terms would be like lambda I minus 1 by sigma square. Lambda 1 minus sigma 1 by sigma square should be 0.
No, not necessarily, right? So these two are conditions independent of pi, right? So sigma I is given by the problem, and lambda I is after all a Lagrange multiplier. Lambda 1 is a Lagrange multiplier. So if, okay, so if, look at this particular condition, if 1 over lambda 1 minus sigma I square is strictly greater than 0, then lambda 1 minus 1 by sigma I square is strictly less than 0. But I have to satisfy the condition that lambda 2I is greater than or equal to 0 for the KKT conditions to be satisfied. But if I choose pi equal to 0 over here, I know that lambda 2I is always equal to lambda 1 minus 1 over pi plus sigma I square. If I now choose pi equal to 0, then this condition is not satisfied. That violates one of the KKT conditions. So really, it's a combination. This pi equal to this is basically a combination of these three, as well as the fact that lambda 2I should be greater than or equal to 0 for all. Any other questions? Right? Okay, so maybe you can have a quick quiz. Do you have your smartphones? Anyone who doesn't have their phones? Okay. So how many of you don't have a phone?
And the second one, do we assume that the objective function is convex?
Saying nothing. The general constraint optimization. Okay, of constraint optimization, it's minimizing. This one. The function may or may not. Done? Is everyone done? Anyone? Sorry?
I'm waiting on the next main one. Switch it off.
Okay. Are you done? Anyone yet to submit? I thought you said you submit. Let's respond to me. Submit. Submitted. Okay, what are the answers?
Convex.
The first one,
Convex.
and it's linear and convex. The second one, it's always convex. Okay, so let's maybe look at an application of formulating and solving convex optimization problems similar to what we've done before. But so far we were sort of given a problem and our goal was just to solve it. The question is, how do you identify the right way of even framing an optimization problem that can be solved? Right? So to do that, let's look at this problem of classification. Right? So what is the classification problem? You are given a bunch of points which are labeled with one of two different colors or two different labels. Right? So for each point, you either label it with, say, 0 or 1. Or in other words, the model that we will follow is the following, that the ground, there's some underlying ground truth which is basically, there are two sets, two disjoint sets. Let's call them S1 and S2. Rn. So any point in the set S1 has label, let's say, 0, and any point in S2 has label 1. Right? But we are not given S1 and S2. Or we're instead given points from S1 and S2. So we're given a bunch of points x1, y1, x2, y2, and so on up to maybe xm, ym. So yi is equal to 0 if xi is in set S1 and 1 if xi is in set S2. Right? So basically we're given the points as well as their labels. The goal is to design some function which I call the classifier, x is in S1 or x belongs to S2 for an arbitrary x. If you recall, this was kind of one of the problems that I introduced in the very first class, right? Not this specific problem, but general learning problem, right? So the goal is to find that f, which kind of predicts the correct class as well as possible, right? In fact, we look at an even simpler problem. So basically, we look at the following simpler problem where f is going to be chosen from the class of linear functions or affine functions, right? The classifiers that we will look at, the class of functions that we will look at, are going to be the following. So f of x is equal to 0 if some A transpose x is, say, less than or equal to b, and equal to 1 if A transpose x is strictly greater than b. Right? So this essentially tells you whether x is in one half space or the other. So we have freedom in choosing A and B, and our goal is to choose A and B so that you somehow get this prediction right. Right? So far so good. Okay. So we'll start with an assumption, firstly, that there exists a good linear classifier. Not that for a given problem, the choice of linear classifier may not be unique. There could be multiple linear classifiers which classify it exactly. So for example, let's suppose that S1 is a ball centered at 0 and has radius 1, and S2 is a ball centered at, let's say, 2 times the all ones vector and has radius 1. What is the distance between these 2 points? Between their centers? Is it 2? Yeah, 2 times square root of n. It's just the norm of this particular vector, 2 times the all ones vector. So it's 2 times the norm of the all ones vector, which is square root of n. And S1 and the radius of these 2 balls is equal to 1. So obviously they're well separated for any n. Right? So for this problem, fine, there is a linear classifier. So pictorially, if you look at R2, then S1, yeah, I'm sorry, the radius. So it's a ball with center 2 times the all ones vector and has radius equal to 1. Sorry?
Distance will be 2 to 2 9.
It's in general 2 root n, right? Yeah. So in R2, the distance is 2 root 2. Okay, so it's something like this. Right, so this would be my S1, this would be my S2. And clearly I can find a line which separates S1 and S2, or a hyperplane that satisfies.
Second one center is 2.
the second center would be 2 comma 2. Right? So this is the horizontal. So there exist infinitely many linear classifiers for this particular problem. So first we'll assume that there exists at least one linear classifier for the two given sets. That there exists a hyperplane which sort of strictly separates the sets S1 and S2. Okay, that's to begin with. Right? And recall that we're not given S1 and S2, but just a bunch of points, right, from S1 and S2. Now, how do we formulate this as an optimization problem? What does it reduce to? Yeah?
Maximizing distances.
Maximizing distances from the plane. Okay. It's even simpler. Let's, when you're saying maximizing distances, you're introducing an additional feature that was not inherent in the problem, right?
Minimize number of misclassifications.
Okay, minimize the number of misclassifications. There exists a solutions for which the classification is 0. Right? Okay, how do you formulate that?
For S1, you just take
Okay, so
so basically for S1, you take the sum, you take all predictions where it's 1, sum of all predictions that are 1 for S1. And minimize this function. Yeah.
okay, so let me call x10 up to xk10 to be the number of points which could belong to a set S1.
So now
These are in
you
set
take the
S1,
sum of all
x1, similarly k2, 1. These points come from S2, right? So you want to do,
So now you define the function as sum over all xi0 such that y is 1.
okay, sum overall xi0 such
Such that yi
no, xi0 is basically the points for which yi is equal to 0.
predicted the f of
The true value of y is equal to 0.
for the loss function I'm saying the predicted value.
Sorry?
For the objective I'm saying the predicted value is 1. You take
Okay.
sum over all those where the predicted value is 1 for these,
Okay.
and plus for the S2 you take the sum over all points where predicted value is 0. So
Um,
1 minus
Sorry. So you want to sum over all possible xi0 such that A transpose xi0
greater than b.
is greater. Let me see the notation that we have. Fine, is greater than b
Plus
Plus
the summation once plus
okay.
summation of 1
of 1
for xi1
xi1.
is that the inverse summation.
Okay, so A transpose xi1 is less than or equal to.
Okay, just minimize this for all.
Okay, so the goal is to minimize this. Okay,
Can we just write this as f of x minus y also?
which one? F of x minus
Like you
1.
want to minimize f of x minus y also. F of x 1 and y 0.
Okay. What is f?
Classifier.
Okay, the classifier. But remember the variables, the variables that I want to optimize over are effectively A and B, right? Which is fine. So doing this would be the same as trying to find out whatever f of x, whether f of x is equal to y or not, right? The corresponding f of xi equal to yi or not. correct? But I have a problem with this, right? This f of xi is not really a nice function to work with, right? So because my variables are a and b, a, x, and b, and this f of x is typically much harder. It takes values either 0 or 1. Ideally, I want something that is that is real value. I want a real valued function. Okay, can we formulate this in a different way? Right now, you're all fixated on the objective function. Trying to tell you, don't look at the objective function. Okay, how would you do this? Yeah. Okay, and what is objective function now? Yeah. So it's a feasibility problem, right? So finding a classifier is the same as solving the following problem. Minimize 1 subject to the constraints that A transpose x I 0 is less than or equal to b for I equal to 1, 2, 3 up to k1, and A transpose xi1 is whatever greater than or equal to b for I equal to 1, 2, 3 up to k2. I still want to keep it greater than or equal to, just to make this a closed set. Right, so this is just a feasibility problem. So if there is a feasible solution, then I get an a comma b, and that is a valid classifier. Right, and is this problem convex? It is convex. I only have linear constraints. My objective function is just a constant. So this is a convex optimization problem, and I can solve this. Right? But now there are infinitely many solutions. Right? If there's a positive distance between these two sets S1 and S2, then obviously I can choose infinitely many. And of course, I'm assuming that there is a hyperplane which separates S1 and S2. And there could be infinitely many possible choices of A and B. So how do we? So now we need the notion of a good choice of A and B, right? So now let's focus on the objective function to be optimized for. Right? Among the class of feasible solutions, let's try to construct a notion of a good feasible solution or the best feasible solution. So let's think about it intuitively. I have two sets. S1 and S2, which correspond to the ground truth, what would be the best hyperplane that separates S1 and S2? Yeah, intuitively.
Line having the sectors and with perpendicular.
Okay, so in some sense, you want to choose a hyperplane which kind of ensures that points in S1 are as far away from the hyperplane as possible, and S2, and the same holds for S2. Right? So in fact, there are different ways of formulating the same problem, but the way we'll do this is, let's assume that we want basically a kind of a buffer between the hyperplane and the points. Right? So really, I don't have S1 and S2. All I have are points from S1 and points from S2. So I have these points which correspond to points from S1, and I have these points that correspond to points from S2. I really don't know what S1 and S2 exactly are. So let me try to construct a hyperplane such that I'm giving some kind of a margin from the hyperplane to the set of points, and I want to ensure that on both sides the margin is as large as possible. Right? So this buffer zone so this is the region where there are no points from S1 or S2, or at least no observed points labeled 0 or 1. Right? And basically the width of the buffer zone is what I'll call the margin. So now I have a new problem. I want to obtain that hyperplane for which the margin is as large as possible. So this is our new goal, which is to construct a maximum margin linear classifier. All right, so this margin can be effectively captured in the following way. So right here, we had the following optimization problem, right? Right, so I wanted A transpose xi0 to be less than or equal to B, and A transpose xi1 to be greater than or equal to B for all I. Right now I want an extra margin. Yeah, a question.
Can an objective variable be inside the constraint variable?
Can an objective variable?
Inside the constraint.
Yeah, why not?
So we have to maximize m where a transpose xi is 0 is less than b plus m and b minus m or
yeah.
the other one is b.
Yes, that's what I'm getting to. So let's define a new variable t, right? So I want to give this extra buffer, which is I don't just want a transpose xi0 to be less than or equal to b, but instead I want a transpose xi0 to be less than or equal to b minus t. I want that extra room. And similarly, if for those labeled 1, I want to ensure that A transpose xi1 is greater than or equal to B plus T. And I want T to be as large as possible. So T is my margin, basically. So I just minimize T such that this happens.
With minus t, right?
I'm sorry. Yeah, I want to maximize T, which is basically minimizing minus T.
We need to add a constraint that t is greater than equal to 0.
Sure, you can add the constraint that T is greater than or equal to 0. But anyway, I'm trying to minimize minus T. That's still okay. But I'll add this additional constraint that norm A is bounded. Which one? That's fine. I'll just say less than or equal to. I just want this to be bounded by some quantity. Not necessary. Yeah, fine. I could impose the constraint that norm A is equal to 1, but fine. I'll just say that norm A is less than or equal to 1. Okay, so now we have an optimization problem. Is this convex? It is a convex optimization problem, right? So that's another reason why I wanted norm A to be less than or equal to 1 and not equal to 1. So the set of all A for which norm A equal to 1, is that a convex set? It's not. Certainly it gives you the same optimization problem, but that is the reason why this is nicer. Right? So basically in any convex optimization problem, the only equality constraints that we're going to allow are linear constraints. We can say that, fine, we could say that B equal to 1. Yeah, that's okay. It's fine. But let's say that we want to solve this particular problem. Right? So this is the problem of finding the best classifier in some sense. Right? So what is the Lagrangian equal to? This is L of T, A, B. I have 3 sets of constraints, lambda 1, lambda 2, lambda 3, which is minus T plus summation I equal to 1 to K1, lambda 1 I. Constraint is A transpose xi0 minus B plus T is less than or equal to 0. Plus summation j equal to 1 to K2 lambda 2j times, so it's B plus T minus A transpose xi0 xi1 is less than or equal to 0. And I have a third constraint that the norm of A should be less than or equal to 1.
So wouldn't it be more convenient to have it as
Norm A square, fine. It doesn't really change. I'm not searching for a closed form expression for this solution. So it's okay to choose norm A at this point. I'm not going to attempt to obtain an analytical solution to this particular problem. But as we'll see, when we look at the dual optimization problem, it gives some insight to, or some geometrical insight into the best solution. Okay, so let's try to compute the Lagrange dual function, or in other words, try to construct the dual optimization problem. So we need to minimize this over all possible T, A, and B. Right. So let's write this out in terms of T, A, and B first. So let's group together the variables involving T. So it is T times -1 plus summation I equal to 1 to K1 lambda 1I plus summation J equal to 1 to K2 lambda 2J plus B times minus summation I equal to 1 to K1 lambda 1I plus summation J equal to 1 to 2 lambda 2J plus the remaining, which is summation I equal to 1 to K1 lambda 1I I0 plus J equal to 1 to K2 minus lambda J A transpose X J1 plus lambda 3 times norm A square. Okay, now if I try to minimize this over T and B, what happens? I'll do the minimization in terms of in 2 steps. First, I'll minimize over T and B, and then I'll minimize over A. Right? So it's a linear function in T and B. So what would the infimum be? T comma B of the Lagrangian. Right, so we have a linear function. What is the minimum? We're taking the infimum over T in R and B in R. Yeah, minus infinity always for all lambda. So it's equal to minus infinity if either of these two quantities are non-zero, right? And it's equal to this quantity if both these quantities are equal to 0, right? And what does this say? So I'll leave it as an exercise, but basically this is the same as saying that summation over I lambda 1 I equal to summation over all j lambda 2j should be equal to a half. And that you can see. So sorry if this is not let me write this differently. So this is equal to some quantity if this condition holds, and it's equal to minus infinity else. So when are these two both equal to 0? When these two quantities are equal, right? So summation over j lambda 2j should be equal to summation over I lambda 1I, and the sum of these two should be equal to 1, which implies that each of these should be equal to half. Right? So if these two are equal to half. And what is this quantity equal to? This is the remaining terms. And now I need to minimize over all possible A. So again, we've done this before. It's basically a quadratic term, and we've computed the dual function of this. But let me just state what it is. So the infimum over all possible A of this particular quantity, this is equal to minus lambda 3 if basically the norm of lambda 1 I lambda 1 transpose it is if summation over I lambda 1 I A transpose lambda 1 I x I0 minus summation over all j lambda 2j x I1 is less than or equal to lambda 3, and it is equal to minus infinity otherwise. So again, this just follows from the property that if you recall long back, the dual of basically a quadratic function or basically a norm ball, a norm was basically the indicator function of the norm ball. This was one of the examples that we did. and so it's equal to minus infinity if it does not lie within a certain norm ball, and equal to some particular constant if it is within the norm. Okay, so now what is the dual optimization problem? So this is equal to g of lambda 1, lambda 2, lambda 3, right? So it's to maximize g of lambda 1, lambda 2, lambda 3, subject to all the constraints that we have so far. So it's maximize minus lambda 3, subject to the following constraints. Firstly, norm summation I equal to 1 to k1, lambda 1 I xi0 minus lambda 2j xj1 is less than or equal to lambda 3, summation I equal to 1 to k1, lambda 1 I is equal to summation overall j, lambda 2j should be equal to half.
Non-negative.
And you have the non-negativity constraints that lambda 1 greater than 0, lambda 2 is greater than or equal to 0, and lambda 3 is greater than or equal to 0. Okay, so if I sort of reparameterize things over here, such that if I instead of looking at lambda 1I and lambda 2j, I look at 2 times lambda 1I and 2 times lambda 2j, right? Then what can you say about this particular quantity? What kind of a combination is this? So even here, let me just do 2 times this, 2 times this, and I take a half outside. I just multiply and divide by 2. And this is 2 times this, 2 times this, into 2. Yeah, correct. So this particular quantity, summation I equal to k1, 2 times lambda 1I xi0, subject to the constraint that this summation is equal to 1, basically gives me a convex combination of the xi0s, right? And this is basically a convex combination of the xj1s, points which are labeled 1. But if you look at all of these, the set of all points for which these are satisfied, then this is like taking one point in the convex hull of all the points labeled 0. So this quantity is basically a point in the convex hull of points with label 0, and this is basically in the convex hull of points with label 1, right? and this is less than or equal to lambda 3. And the goal is to basically maximize minus lambda 3, or in other words, minimize lambda 3. So minimizing lambda 3 is the same as minimizing this particular quantity. Right? So what is the minimum of this particular quantity on the left? What does it geometrically represent? Yeah. So it's basically half of the distance between, half of the minimum distance between the two convex hulls. Okay. So we're given a bunch of points which are labeled. So these are points which are labeled 0, and these are points which are labeled 1. Right? If you look at the dual problem is the same as minimizing so the dual problem is the same as minimize this subject to these two constraints, right? These constraints basically say that the two lambda 1 i's and two lambda 2 j's should be convex combinations. Right? These constraints basically say that these are convex combinations. Right? So effectively, this is a point in the convex hull of the yellow points. And the second term is basically a point in the convex hull of the green points. And the minimizer would basically be the minimum distance between these two sets. Right? In fact, half the minimum distance between these two sets. And what does that correspond to? Right? So maybe this is the half, this is the point which corresponds the closest point from this set, and this is the closest point in this set. So half the minimum distance would basically be the midpoint between the two convex hulls. So what does this tell us about our classifier? That the optimal classifier. The optimal classifier would basically be a hyperplane which basically goes through the midpoint of the convex hull between these two sets of points. And that's naturally expected, right? Because after all, if you want to maximize the distance, if you want to maximize the margin, then you also have to maximize the margin to the convex hulls of these two sets of points. Again, that's purely because you're using a linear classifier. And this would basically correspond to the margin. So the minimum distance between the convex hulls corresponds to the maximum margin. question?
From the last minimization function, we just get the this is the minimum half distance.
Half of the minimum distance, yes.
And this corresponds to the closest points, right?
Correct. That gives the closest points, but essentially corresponds to the midpoint of.
How do we get the line from this?
How do you get the line? Again, it's geometric interpretation more than anything else. But these, well, you would have a point over here, and corresponding to this point, the closest point in the other set. Right? Let's assume that the distance between these 2 points is the minimum distance between these 2 convex hulls. Right? So this would basically be the normal to the hyperplane that separates these 2.
How do we get the normal property? How do we know the line should be normal to this?
The line should be normal to this. Anything else, if you think about it, is going to have a worse margin than this. Right? Makes sense?
We assume the test set will be the convex.
Which one?
Test set will be the convex of the test
Oh, the test set will be in the convex hull.
of the test.
So we're not testing anything yet, right? We're just given this.
The set S1 and S2 are approximated sets. So basically,
In general, yeah, they would have to be convex. Or at least the convex hulls would have to be separate, linearly separate. So let's stop here. Any questions?
you said the most
I'm sorry, I didn't hear you.
you said that the lecture will be
Correct. It's the same thing. I've just updated the file.